Good morning, good afternoon, or good evening, whenever you get the chance to watch this. My name is Karin Menendez Delmestre, and I work at the Valongo Observatory, the astronomy department of the Federal University of Rio de Janeiro in Brazil. I'm going to turn off the video now in the interest of space, and wanted to thank the organizers for giving me the opportunity to tell you a little bit about the work that we have been developing in Rio. So I'll be telling you about projects that are come together to map stellar mass in nearby galaxies in an effort to understand how dark matter is actually distributed in our own galaxy. But let's go little by little through these details. So first, the main interest here and the main focus of nearby galaxies is due to the fact that they really represent the fossil record of galaxy evolution. They are the result, nearby galaxies are the result of all the things that have happened through cosmic time, how gas has actually collapsed into dark matter potential wells and have actually formed structures and filaments, etc., etc. And here I'm showing you an image, an illustration of 75 nearby galaxies that compose the SING survey. So you can actually see the main thing that I want you to take away from this is that there's a great variety in shapes, in galactic structure. You see disks, you see spiral arms, you see bulges, you see just balls of gas, pretty smooth. You see some irregular galaxies too. So any model of galaxy formation and evolution must be able to reproduce these characteristics. So nearby galaxies represent a very important benchmark to test any and every model of galaxy formation and evolution. So our interest actually here in the context that I'm presenting this to you is to use luminous matter actually to trace the distribution of dark matter. So if you consider the large scale structure here, I'm just showing you a slab of the Illustris cosmological simulation. You can actually see here dark matter. This is a zoom onto dark matter structures, and you can see how they correspond. In the centers of many of these great concentrations of dark matter, you can actually see galaxies. So we can use galaxies and luminous matter in general to trace dark matter, much as the way that you can use the lights on a Christmas tree to get a sense of the shape of this Christmas tree. And each galaxy is actually immersed on a galaxy on a dark matter halo with subhalos associated to satellite galaxies, or perhaps not even occupied. But you can actually then use the distribution of stellar mass, so stellar matter, to understand how the dark matter is distributed. So the ultimate objective here to make connection, really connecting us literally here to Earth, is to do a careful characterization of how the stellar mass is distributed in galaxies so that we can isolate and disentangle the distribution of dark matter from total matter. So, so in this manner, we can actually construct a more realistic profile of distribution of dark matter and get a sense also of what the local density of dark matter is. Now, there are other ways of doing this too, but here we'll provide an additional, an alternative way, looking at external galaxies. So by looking at Milky Way-like galaxies, we can actually understand what the typical distribution is in spiral galaxies, galaxies such as our own, and we can fit this information to experiments here on Earth, and here I'm showing specifically the LZ direct detection of dark matter experiment, because we have actually started a nice collaboration with the group in Coimbra. But the idea really is to provide these parameters, the local density of dark matter and a more realistic dark matter profile, in order to allow for better predictions of the number of events that they can actually expect. So there are a number of direct objectives. So this was the broad context that I presented to you, but now the direct objectives, like the goals that we have, is first we need to get a very loyal view of stellar light in galaxies. So we need deep imaging to trace stellar light. And the best region in the electromagnetic spectrum to look at stellar light in galaxies, even in regions where there's a lot of dust, where optical imagery really fail at letting us know where stars are located, really is to go to the infrared. So many studies in the last decades, where we have been developing many infrared facilities, telescopes, point us in this direction. So dust extinction is actually minimal, so it's quite transparent view to dusty regions when we go in the near infrared or mid infrared, as I'll tell you in a moment. But also the infrared light is dominated by old stars. And here I'm talking about the near infrared and part of the mid infrared. So old stars, they may actually be the less massive, but they're more numerous. So they really do trace the bulk of stellar mass in galaxies. So the Spitzer survey of stellar structures in galaxies, or S4G as I refer to it in the, from now on, the PI of this survey was Kartik Sheth. This survey was one of the main legacy programs from the Spitzer, the Warm Spitzer mission. So this actually comprises a volume, magnitude, size-limited survey of more than 2,300 nearby galaxies at these IRAC bands, 3.6 and 4.5 microns. So these are images, deep images down to 1 solar mass per parsec square of all basically large, bright galaxies out to the Virgo cluster, so out to 40 megaparsecs. So you have thousands of galaxies, I mean, more than 2,000 nearby galaxies that are imaged to exquisite depth. So really, this makes the S4G the largest, deepest, most homogeneous survey of nearby galaxies in the mid-infrared. And here, just to show you, this is in this image, the first row, you can actually see the images from S4G for these 3 galaxies. And these 3 galaxies also imaged by the 2-micron all-sky survey, which was what we had before, which is a really great all-sky near-infrared survey. But that it was a shallow survey. We learned a lot about galaxy. We continue learning a lot about galaxy evolution, but S4G, you can actually see how it surpasses greatly in terms of depth. I mean, S4G is done from space to mass from the ground. So although I'm telling you that 3.6 and 4.5 microns are excellent bands to trace the stellar light, there is still some contamination by young stellar populations. And for that reason, and just to be a little bit more detailed, you have excitation of molecules called polycyclic aromatic hydrocarbons, or the tiniest pieces of dust already at the molecular size. So they get excited and they have by UV photons from young stellar regions, and they excite and they emit at 3.3 microns, and that can actually contaminate the 3.6 band. So to actually get a very clear conversion from stellar light to mass, we need to do spatial resolved analysis of stellar ages. So to know which parts of the galaxy contain young stars, which galaxies contain old stars, so that we can really do careful characterization of the distribution of stars. So for that, this is where the Kanga survey comes in. So this is the Census of Austral nearby galaxies. This is a survey that we have started 2 years ago already at Valongo. So the PIs are Thiago Signorini Gonzalez and myself. And we have been working very closely with a number of other scientists in Valongo, including students, postdocs, and visiting professors. So this is the main thing is deep imaging in 4 filters. So the GRIS filters using the SOAR telescope, the Goodman imager. I can actually tell you just very qualitatively. You can actually see, if you look at the images of this galaxy, you can see that as you go to the redder bands, you see very little of the disk. While if you're in the bluer bands, you can actually see a very prominent disk. This points us to a bluer disk, younger populations of stars in the disk. So the idea is to do spatially resolved stellar population analysis, but actually not so qualitatively, but much more quantitatively. And this is the idea. What we're doing, because we've been doing this already for 2 years, is go down to the same depth as S4G in terms of mass, so down to 1 solar mass per parsec square. We're doing this for over 1,000 galaxies. All S4G galaxies in the southern hemisphere will be included in this survey. So this is a long-term commitment, and we are building Kanga to be the largest, deepest, most homogeneous survey in the optical for southern galaxies. So what we do is combine S4G and Kanga photometry, so that we can actually map the galaxy spectral energy distribution at each pixel, and we can really study stellar populations at subgalactic scale. So here I'm talking about tens to hundreds of parsecs. So really galaxy formation in 2D, which is very exciting in itself. Here, just to give you an example, you can distinguish between regions in the close to the spiral arm and closer to the center. You can actually see how redder, these are the points, the photometry from Kanga. And if we comparing to a set of empirical theoretical libraries, we can actually say something about the age, about many other things about the stellar populations. But here I'm just concentrating on the fact that we can actually see that there are older populations, older stars in the close to the center of the galaxy, and younger stars in the spiral arm, which actually is very consistent with what we understand about how galaxies form. So this is a kind of map, just in a more detailed manner. If we actually run this pixel by pixel for using the LIFAR fitting algorithm using the S4G and Kanga photometry, we can build this star formation map, so we can know how many stars, how many solar masses are being built per year in each region, and we can actually build these stellar mass maps. So this is the idea, and what we actually have been doing already, I'm going to show you a few results. What we do is exploit the S4G 2D decomposition of galaxies. Here I'm calling the attention to work by Salo 2015 from the S4G team. And you can actually see how you can actually, by taking an original galaxy, you can actually build a model. In this case, it contains a disk, a bar, and a bulge. You can actually see how it is here in more detail. You have a bar model, a bulge model, a disk model, the total model, and you can actually just subtract it and explore also the residuals. In here, you can actually see exquisite residuals from NGC 1097. You can see the spiral arms, a little bit of the rings, etc. So we're using that to look at different populations of galaxies. This is work here done by Bia Ramos, who used to be a postdoc in our team. She's no longer in astronomy, but she continues in contact specifically for this really nice project that she developed. But just to tell you a little bit about these red-ended galaxies. So these early type galaxies, this includes elliptical galaxies, which usually are just thought of as a ball of gas. I mean, very passive, smooth. They're lenticular galaxies that have a disk, but usually there's not star formation associated to them, very little dust. So it's kind of like the very basic way of describing them is that very smooth, passive, not much happening in them. However, we see, I mean, this was work by Taeyeon Kim from 2012 and the S4G team. We saw that close to 20% of early type galaxies display peculiarities. Here I'm just showing you a really nice example, one that had been known way before because it's very extreme. And you can actually see that there are shells and very sharp structures that deviate from this very smooth looking galaxy. If you actually subtract the model for this, the main model of a smooth galaxy, in this case, you can actually look at the residuals. Here are the residuals from the S4G image, here in the UV, near UV from Galax, and here UG RIZ. This is in the optical. In this case, it's from the Sloan Digital Sky Survey, but it's the kind of thing that we can do also with Kanga. And what we did was stellar population analysis specifically on these shells. And what we find is that less than 10% of the total mass of the galaxy is contained in these shells, as you can see here. So all of these shells. And they are not associated with active star formation, but they are consistent with the persistence of shells associated to a star formation event that happened 1 to 3 billion years ago. So this is very nice work that we should be publishing at some point soon. So stay tuned for that. On another subject, we have actually also been looking at the tiniest galaxies. So instead of the most massive galaxies, as I just showed you, the red-ended galaxies, we're looking at the tiniest galaxies. These are dwarf galaxies. They're the less massive galaxies, so less than 1 billion solar masses, but they actually dominate the universe in terms of numbers. And this work has been mostly moved along by Yasmin Coelho, an undergraduate student, and Marco Grossi, visiting professor in Valongo. And what we did actually was looking at 400 dwarfs in S4G. So this is a statistically significant sample that we're looking at. And work, for instance, that we're bringing into the team, into this part of the work, Cynthia Herkenhoff, another undergraduate student at Valongo. She's actually from mathematics, but she's participating in this work. we see that they seem to be consistent with just regular star-forming galaxies. So this is a plot showing star formation as a function of stellar mass. And generally, I mean, this red line shows us the main sequence of galaxies at local universe. And all of these points are S4G points, with the light blue ones being the dwarf galaxies. And you can actually see that their behavior is pretty much along this red line. So their behavior is very much like typical star-forming galaxies. The dark blue, just to point you to them, these are the Kanga galaxies that we have already observed. So what we find is, if we look at the 2D decomposition, we see that most dwarfs, so 65%, are pretty well fit by just a single disk. But very interestingly, is that 11% display bars. So this is very low compared to massive galaxies. In massive galaxies, we find 65% of galaxies show a bar. And this is actually a question that has been posed before by other works also that have been looking at this. Here, looking at the S4G sample too, Peter Irwin looked at this and found this scarcity of bars. And there are many possibilities. Here I'm pointing you to work by Lia Tanasula, just different simulations that point to the possibility of how galaxies may be hampered in their process of forming a bar, because usually a disk will naturally come to form a bar, unless it is too gas rich, or it's too dynamically hot, or there's the dark matter distribution is more centrally concentrated. So the jury is still out of why bars are so scarce in dwarf galaxies. But the low fraction that we measure is consistent with the trend that dwarf galaxies is where the action is happening in terms of bars. I mean, they're still in the process of forming their bars. And interestingly, this is something that is new from our work, is looking at the stellar content, the mass content in these structures. And we see that roughly 10% of the mass is contained in these bars. And this is similar to what we find in massive barred galaxies, which is quite interesting, because then we have few galaxies that do contain the bars, but those that do contain, they seem to involve the same amount of matter in the galaxy. So, but looking a little bit into the future and connecting us here to the dark matter context that I posed initially, the idea is, we have more than 1,000 galaxies that we'll be looking at with Kanga, and we are looking forward to hundreds of spiral Milky Way-like galaxies. So these galaxies with spiral arms, with similarly star-forming galaxies. I mean, so we are looking forward to many analogs of Milky Way galaxies. And the idea is that by having a very careful determination of the stellar mass distribution based on S4G and Kanga, we want to use then rotation curves. So these rotation curves that I'm showing you here, they're usually based on H1. So this is atomic hydrogen that allows us really, if you see in these images here, this is in the optical, but if you look the atomic hydrogen really is to the same scale, it really stretches out to peripheric regions. So we can really get a sense of what the motions, the dynamics are in these extended regions that we don't see at all just by looking at the stars. So by having a really nice mapping of stellar mass, we can really disentangle the dark matter component. And in that sense, we can create dark matter profiles for these galaxies. And by having several Milky Way-like galaxies, then we actually can draw analogies to our own galaxy. So we're starting this with just a couple of galaxies this is work done that we're developing with Nathaniel Oliveira, another undergraduate student at Balongo. And the ultimate goal, as I said, really is to construct a more realistic dark matter halo for our own galaxy and establish a number for the local density of dark matter in the solar vicinity. And this is something that we will achieve as Kanga continues to grow. Just to take home message, just closing in here, we are looking at mapping the stellar distribution, the stellar mass distribution in galaxies. S4G actually does show a really nice, the bands of S4G, you can actually use them almost ideally well to trace stellar mass, but we need Kanga, we need deep optical imaging out to the faintest regions of galaxies to trace the stellar populations and really eliminate contamination from young stars so that you can really trace the stellar mass distribution and ultimately disentwine the dark matter components. So we have 50 galaxies done, more hundreds to go, so stay tuned. And just finishing up here to provide you some information to get in contact with me. And if you're looking for postdoc opportunities and you think you can deal with this view, please do contact me. Thank you very much.